Hello, I'm Laura Cassidy from the American Chemical Society. Welcome to this news briefing from the American Chemical Society Spring 2019 National Meeting in Orlando. We're joined today by Dr. Thomas LaGrasso from Ames Laboratory. He's studying new alternatives that may ease the demand for scarce rare earth permanent magnets. Dr. LaGrasso?
Thank you, Laura. So I represent the Critical Materials Institute. This is a Department of Energy Innovation hub that is a multi-institutional, multidisciplinary approach to addressing criticality of elements and materials that are important for clean energy technologies. There are three strategies: diversifying supply, trying to find more of the materials we need, developing substitutes, alternatives for the materials we can't live without, and then recycle and reuse. In our area that I oversee, it is developing substitutes, and currently we've worked on two problems: lighting, fluorescent lighting, and phosphors that are used in that technology, as well as permanent magnets. Today I focus on permanent magnets because permanent magnets are ubiquitous. Everything, if you will, from your refrigerator magnets to the motors in your car to your cell phone vibration, everything depends on magnets. And in particular, the high-powered magnets are made of critical materials: neodymium and dysprosium, two rare earth elements. And those rare earth elements actually are abundant, but they are processed mostly overseas. The U.S. does not have any supply chain capability for magnets for the neodymium iron boron. And so while that market for neodymium and dysprosium as pure elements is small, just maybe on the order of 1 to 2 billion, by the time you make a magnet out of that market increases by a factor of 10. And then when you consider how those magnets are used in automotive applications and other applications, that market becomes very large. So the work we do can have a significant impact, whether it's in your vehicle and importantly in the next generation of vehicles as we electrify our fleet, to your cell phones, to your earbuds. All depend on magnets. So we've used a number of different techniques to look for alternatives to the high-powered rare earth containing magnets that include both computational searches, high throughput and rapid assessment of experimental means to find new materials, and data mining and machine learning, combing through the literature. And today I kind of want to focus on that data mining aspect that has led to kind of a unique way of looking at trying to find new magnet materials. So the case that I want to talk about is Cerium Cobalt 3. And it's this case of looking for something in an unexpected place. You might, if you're an automotive person, you might say, well, this is the barn find. You know, you go into a barn, you find this old jalopy, and it turns out to be something amazing, and you restore it. Well, Cerium Cobalt 3 is kind of like that. It's in the literature, and it turned out to be a paramagnetic, that is non-magnetic, and it's typical of exhibits polyparamagnetism. Basically, it doesn't stick to anything. But it should. It's got 75% cobalt, and cobalt's one of the strongest magnetic elements around. And so the team looked at that and said, well, that's really strange. Why? Why doesn't it form? We could have easily walked past it and said, oh, it's not magnetic, so let's not worry about it. But they looked at it, and it has that feature, the features needed for a permanent magnet. It has the high cobalt content, which suggests a high degree of magnetism. And it has this crystal structure shown to the right of a non-cubic crystal structure. And what that means and why that's important for a magnet is, I think we're all familiar with a magnet having a north and a south pole. And what that means is that the moments the moments on the electrons on the atoms are all pointed in one direction. So you get a north and a south pole. And we like that, we call that anisotropy, and it's prevalent in these non-cubic structures. So cerium cobalt 3 is orthorhombic. And so it has this long c-axis as depicted. And ideally, then, we want the magnetic moments to be aligned with that long axis. If they are aligned in the perpendicular, then it's not it's called planar anisotropy, and it's not as promising for a permanent magnet. What our researchers then did was say to themselves, this compound seems to have lost its way. So let's rehabilitate it. Let's try to change its chemistry and make it ferromagnetic. And so they've coined the term rehabilitation as a methodology of taking a element for all, or a compound that for all practical purposes should be a desirable magnet, and let's start to change the chemistry. Let's tune it. So again, looking through the literature, there are reports of adding magnesium to this compound for hydrogen storage. So they started to do that. And the next slide shows the result. Plotted here is the magnetism as a function of temperature. This is done on single crystals. And this is more of an intrinsic property. Permanent magnets rely on extrinsic factors to make them permanent magnets. But at first they have to have the intrinsic properties before you can make them into a permanent magnet. So this is an intrinsic property. It shows the magnetization as a function of temperature. And as you cool the material, the magnetization will first show a stark increase that's associated with the Curie temperature, or the temperature of the onset of magnetism, and then it increases the further you go down. And what we show here is the effect of adding magnesium to this compound. Now, the Curie temperature for just cerium cobalt 3 is non-existent, so it's essentially 0 Kelvin. But as we add magnesium, we reach a maximum content of replacing approximately 1 1/3 atoms of cerium with magnesium. And at that point, the Curie temperature rises to about 435 Kelvin. So just above room temperature, a little bit higher than room temperature. And that shows some promise. The next question is can we turn that intrinsic property of that material into something that can be used, suitable, permanent magnet? And the experimental results are in, and indeed it shows the features. It has coercivity, which is a measure of the resistance to demagnetization. It shows a high enough magnetization. It's not going to replace neodymium iron boron, unfortunately, but it does have a particular potential for niche applications. So it can replace maybe some of the low-end magnets. There is a certain performance level where only rare earths can be used, and so this could be what we've called a gap magnet. That is a magnet that would be useful between the non-rare earth bearing magnets and the rare earth bearing magnets. Right now, if you're in that middle, you have to use a rare earth. This could be a potential displacement magnet that would give you an option not to use the rare earth and thereby reduce the criticality.
Thank you, Dr. LaGrasso. Are there any questions? Please state your name and affiliation before asking your question.
So it's Kath O'Driscoll from Chemistry and Industry magazine. When you say these could be gap metals, gap replacements, what types of applications do you mean? And could you give an indication of by how much we could reduce the demand for dysprosium or neodymium or some of these rare earths by using these things?
Sure, thank you. A gap magnet is a magnet that, as I mentioned, between kind of the non-rare earth bearing and the rare earth bearing. Application space for this could be automotive applications where you either actuators, sensors, or motors where the power requirements are not particularly high. So it could be a motor for powering your window. Right now, if you want to minimize the size of your motor, you'll go to a rare earth bearing motor because of the strength there. Your alternative is probably something that's on the order of 4 to 5 times the size using non-rare earth. So getting a gap magnet allows you to play that size versus power. And in doing so, if you can reduce the size of motors and actuators, then you're lightweighting, so you get an advantage in the mileage and lightweighting of the vehicle. That is twofold. One is you're putting in a lighter component, but you can also make thinner, say, door panels if your motors are not as large. So there's multiple benefits. It's a little bit harder to judge how much we would displace neodymium in these sort of applications. Truly, we do techno-economic analysis, and we try to estimate that because, again, we want to work on finding suitable substitutes, and so it's a bit of a challenge to estimate that. My guess, and maybe it is a bit of a guess, is that I guess how do we do this? By tonnage, that maybe we could replace on the order of 10,000 to 20,000 tons of neodymium with the development of a suitable gap magnet. And suitable is an interesting word. I choose it carefully because we can identify candidates that are substitutes, but then we have to consider all the other aspects that a magnet material must meet besides just the magnetic performance. There's corrosion, there's fading with temperature and time, and cycling. And so our goal is to develop a suitable magnet material that could substitute, and then we rely on our industrial partners really to develop that material into application space. Yeah.
Charles Berquist, Science Friday. Broadening out a bit, what would some other examples of critical materials be? What other things are you looking to get rid of or replace?
Sure, thank you. Actually, in the lighting, well, maybe I should start out. Other examples of critical materials depends on who's asking the question and what it is that is of particular importance to them. For clean energy technologies, for the Department of Energy, we focused also on lighting in addition to permanent magnets. In the lighting arena, europium and terbium are two rare earths that are critical, and they are present in the long tube fluorescent lighting, which still has a lot of application space. Now, the lighting in this room may be LED, but where I gave my talk this morning, it was definitely long tubes. They're the red light. So fluorescent lighting uses a tricolor phosphor, red, green, and blue. The blue is relatively rare earth free. The red is europium, and the green comes from terbium emissions. We replaced both the red and green with substitutes. The green, we were able to reduce 90% of the terbium use. With the red, we found a aluminum nitride-based substitute with no rare earths. Those working with our industrial partner were discovered and brought to kind of manufacturing trials within 3 years, which is remarkable. We're very proud of that achievement. Other areas that are a little bit more challenging as far as critical materials for clean energy, of course, energy storage. Right now, lithium, cobalt are two particular elements that we should be concerned about because of the electrification. Where does the lithium come from? How do we ensure a supply? The cobalt, actually, from a substitution standpoint, there's been a lot of work. And maybe the substitution strategy is not appropriate for cobalt. But the recycle reuse is. And if we could take our spent batteries and be able to recover the lithium and the cobalt, then we can ensure a ongoing supply other than digging more ore.
Okay, Katie Cottingham from ACS. I was just wondering, how long do you think it'll take to get your magnets into practical use? Do you think?
Great question, Katie. The challenge is always trying to accelerate that process. I'll be honest, our magnet team, because there is no domestic supply chain, it's made it difficult to engage industry in the way that we were able to engage industry in the lighting area. As a result, it's been a little bit longer, but the problem is a lot tougher than it was in lighting. Magnets, our current palette of magnets that people can choose from in terms of designing electric machines has been fixed for about 40 years. There's been some incremental improvements, but there's been no breakthrough. And so, trying to find a new material that can fit into an existing manufacturing process, that it's i.e. process compatible, is really the key to determine how quickly you can deploy a new material. Most manufacturing firms, I don't want to necessarily say are risk avoidant, but even the early adopters aren't going to make a large capital investment if they have to create a new process to create a new material. So it's a balance between having a process compatible material. Drop-in substitutes would be great. We don't always have that choice. Mother Nature tends to limit us. And then having an early adopter. Those are kind of the factors that determine the pace at which material will transition to the marketplace. I think the key successes we've had over the first 6 years of CMI is always targeting our technology development to specific applications. So in the lighting, it was fluorescent lighting at first, and having demonstrated a methodology that works, we went to LEDs. And we've developed some nice technology to make the LED more tunable from a color standpoint, so it's not always this stark blue light. And the team has had great success there. We're taking that methodology and translating it to magnets, and maybe in our next few years we'll transition it to electrical storage.
Bela Buswig, American Chemical Society. What are the economic advantages of cerium cobalt-based magnets as opposed to the, and the other question would be, is what our size differential, because obviously one, for the same strength of material, one is different from the other.
Sure, great questions. The cost for, so cerium is the most abundant of the rare earths. In fact, you would really characterize a rare earth mine as a cerium mine. So relatively speaking, the cost of cerium is much less than neodymium or any of the other rare earths for a couple factors. First, cerium is the first rare earth element you separate. In the sequence of separations, it is sequential, going from the lighter rare earths to the heavier rare earths. So cerium is the first one, and if all you're after is the cerium, then the operation costs are down. It's a factor of, well, the cost of cerium, I don't have the current pricing in my head. It is less than neodymium, but there is an oversurplus of cerium. And so while we still consider it to be a critical material because the source is still limited, there is an oversupply. The more troublesome element in this composition is the cobalt. And cobalt's been fluctuating widely. Of course, it's being driven by energy storage, and so we are conscious about that. When we kind of compare the raw material costs, we're on par with neodymium iron boron with dysprosium additions. So it's kind of break even. Yes, there's a loss of performance. As far as processing costs, it's about the same as neodymium iron boron, although there may be some processing advantages to cerium cobalt. So we haven't struck out on cost yet. And again, that has to do also with the application space we're targeting. So your second question was?
The second question had to do with size differentials. For the let's assume an electrical motor. One is powered by rare neodymium samarium or something, or the other one this particular kind of material. How big the differences are?
So it's going to be so you design an electric machine based on the volume, or you choose the magnet volume based on the size of the energy field you need, and that tends to be on the order for cerium cobalt. It will be on the order, or for a gap magnet, to be honest, a gap magnet will probably be on the order of a factor of 4 to 6 increase in size. Right now, your alternative is to go to the very high power neodymium sintered magnet, or to use what they've called a bonded magnet, where you take the neodymium powdered material and you place it in a polymer binder. Now you have some limits with temperature use, but you can reduce the amount of neodymium iron boron to get into that range where you're just you're not oversizing the magnet or oversizing the motor. It's a trade-off between lightweighting versus
Would there be any possibility of kind of using a hybrid system with some of each kind of magnet to perhaps use? I'm kind of going out on a limb here, but is there any such thing as a hybrid magnet system?
Yes, and not so far out on the limb, actually. So there's two hybrid systems that I think have gained traction. The first is taking neodymium iron boron centered magnets, and what determines a limitation on that is what's termed the coercivity, the demagnetization force. And for neodymium iron boron, at temperatures above 120 or so, it begins to lose magnetization. And the way you preserve that is to add dysprosium or even terbium. But you don't need it in the center of the magnet. Where you need it is on the edges, where the demagnetization forces are the largest. So if you could just put the dysprosium just on the corners and here and there, and they've developed technology to do that. So they'll make a neodymium iron boron magnet, and then they diffuse dysprosium into those key critical areas, thereby saving the dysprosium. So that's one type of hybrid processing one can do. The second type of hybrid is mixing, say, a very strong permanent magnet with a softer magnet. This is called exchange coupled spring magnets. it's tricky because in order to gain a benefit, you take the hard and soft materials, that is hard magnets and soft magnets. So a hard magnet is neodymium iron boron. A soft magnet, for example, could be iron or cobalt, or a mix of the two. And you mix them together, and you mix them such that the size of the particles are quite small, tens of nanometers. And if you can get those mixed appropriately and distributed uniformly, what the hard magnet material does is it coerces, it forces the soft material to line up. And so you take something like iron that has a lot of magnetic moment, but it's soft, so the moments can go any which way. And you put it in the vicinity of a hard magnet, and you align all those magnets. So now you get your hard magnet moments and your soft magnet moments working together, and you get a better magnet. There's lots of difficulties in trying to do that from a synthesis standpoint. And we have programs in CMI to work on this, and I know there are many people working on this. High-risk project, but the rewards are high.
Thank you, Dr. LaGrosso. I'm
Sure.
sorry we're out of time, but
Okay.
very fascinating. The archive version of this session will soon be posted at bit.ly/ACSlive_Orlando 2019. Please join us for our next press conference at 1:30 p.m. today on minimizing fuel explosions and fires from accidents and terrorist acts with polymers. Thank you.
Thank you.